Good afternoon. I hope everyone had a nice lunch. Apologies for the delay. We have a very excellent panel of speakers this afternoon, speaking on a variety of technical topics, and we're going to hear from people that are on the ground in the trenches and doing amazing work in a variety of very applicable topics. So hopefully we'll find things that are practical that we can really learn about and take back to our own institution. So let's kick it right off with Jim Lindner. Jim is no stranger to Symposium for many years, and I think we all know Jim well. His expertise runs vast, and so I'm just going to hand it right over to Jim and kick it off.
Thank you. Hello, everybody.
Hello.
You're kind. I think this is going to be a lot of fun, and we'll see what happens. For 25 minutes, I think I have 35 slides, so we'll be going quickly. The bottom line is, as all of you know, there's just too much film. There's too little time. And it's not just one thing, it's a whole bunch of different things. The film continues to deteriorate. We talk about end of life for film, but how do you define end of life for film? It's really hard. But what we do know is we do know that it gets worse every year, right? It's great to have a cold vault and it's great to do all of those kinds of things, but the film isn't going to get better. It's just going to get worse slower. Along with that, we have, what I call the film industry implosion. Most of us figured out a long time ago that Kodak wasn't going to survive, and they didn't. They went bankrupt. They've come back, but we sort of thought film would disappear. The stuff disappeared, and it's actually had a resurgence. Some of the young people like shooting film, believe it or not. But there's a whole bunch of other stuff that didn't survive, which we didn't think about. So things like projectors. Companies that make projectors, companies that make the parts for projectors, and the light bulbs, and the sound systems, and all of the other stuff, and the systems that play back mag full code, and all of the production systems, the stuff that were in labs, all of the lab processing equipment. That industry is basically gone, and it's not just that the equipment is gone; it's that the people who knew how to run it are gone too. They all have hair like mine. Most of them have retired, or they're just not around, period. My daughter went to the MEOP program at NYU. She graduated 2 years ago, and no one in her graduating class that I know of went to work for a film lab. Young people are not going into that part of the industry, so the expertise is becoming unavailable. And the obvious digital accessibility is required. That's how people expect to look at audiovisual materials on their computers. That's what they expect to do. And of course, the cost of migration increases over time. Crazy idea, but people want to make more money next year than they did last year, right? So things aren't getting cheaper. And so really in 2015, I started a project called the Filmic Project. And the Filmic Project, and I presented it at CIPAVA and at JTS and a bunch of other places. And the Filmic Project was an attempt to sort of look at, from a purely clean piece of paper, how can we preserve film in a purely digital way, not based upon what everyone did in the past. And so we did that project, and there was a lot of participants in it, and we made all of that information public. And I kind of expected that the people in the industry would go, oh, there's a couple of ideas here we can use, let's do that. They didn't. And so, about 5 years ago, 4 or 5 years ago, it became obvious to me that people weren't going to do it, and, then I would have to do it. Because film's too important to just, let go. And so I started a project. Now, some of you, when I was thinking about starting it up, I was like, well, what was I going to do? And That picture of a robot, that was my previous invention that I did with, when I was working, I was a consultant for the Library of Congress and designed their system. And the only way to process the work was to figure out a way using workflow to dramatically increase the productivity of the normal way of doing things. And so my first obvious thing was, well, I'll just do a robot for film. Well, you don't have to go down that technical road very long before you realize that it's not such a hot idea. The nice thing about videotapes is that they're all in cassettes, and there's all machines, right? And so you have all of those things sort of lined up. You kind of know what a pneumatic tape is going to be. You know the size, you know, all of that other kinds of stuff that you don't for film. So we had to really look at it differently. And so the questions became from sort of an engineering standpoint, what do we want to do and how do we want to do it? Like what do we want it to be, and how are we going to make that happen? And hopefully, I know some of you have in this room, the result, one of the results of all of this work and all of this time is actually in the ballroom. And that's the EZ16. We went through several different versions. I know there's at least one person in this room who had an FI16. That was the one before. We actually went through several different versions of the machine before we were able to sort of figure it out, get it right. This is not easy stuff to do. And so you learn along the way. So what did we want to do? Well, we wanted to make it easy to, we didn't want to look at other film scanners. This is like next generation thinking. And there's next generation tools. We're not going to like do it the way people made things 20 years ago. We're going to use modern tools. We're going to use, the whole system is designed CAD-CAM. It's called fast prototyping. You don't do one thing and send it to a machine shop and get it back 6 months later. You 3D print it, you try it, you make one part, that doesn't work, you make another part. We designed all of the circuit boards ourselves. We couldn't buy what we wanted. We had to actually build it. So what were we going to build? Well, first of all, it had to be easy to use. We wanted the machine to have the expertise because we realized the expertise was disappearing. And so it was really important to have it easy to use. And I'm kind of proud of one thing that, sort of a side benefit, which we didn't anticipate, but we have an office in Baton Rouge, Louisiana, where the machines go out and their customer service and all that. And the person in charge of that, his name is Jimmy, has a son who's developmentally challenged. And after school he goes to work with Dad, right? And his son has learned how to run the machine. And so what happens is the teachers for his class came over. He's like 16 or 17 now, and he's severely developmentally challenged. And the teacher asked, well, whether they could bring more of the students over to learn how to do it, because people who are developmentally challenged have trouble getting jobs. They have trouble doing certain kinds of work, and this is kind of work they can do. And so it's simple enough that people who have like significant challenges can actually use the machine. And that's, for me, that's a huge check mark. I mean, it's kind of amazing that we could do that, and I feel lucky that we were able to. We wanted the machines to be much less expensive. Doesn't mean cheap, but it sort of influenced the way we did the design, and I'll show you that in a couple of minutes. We wanted it to be small. None of this stuff comes in a big wooden box and someone has to come there and set it up. It comes in two cardboard boxes. It comes by FedEx, or DHL. And you open up the box and put it on the table, and there's like 4 wires, and you plug it in, and that's it. It's self-contained, and if you've seen it inside, you can actually put it on a cart and bring it to where the film is. It has a server built into it. So all of the stuff you need to do film scanning is built into it. If you have an outside network, that's fine, but if you don't, there's storage in the machine, and they're removable drives. So you can just take the drives out, sneaker net, and put them into another machine somewhere else. We want it to be rugged. A lot of these kinds of machines in the past have been very fragile. And so we wanted it to be a rugged kind of a machine that was easy to install and repair. And we wanted it to scan just about everything. I won't say everything, because that's a big everything. But we wanted to scan, like for instance, it does mag tracks, film with mag tracks. Right? And to give you an idea of how hard this was, there's one company in Europe that makes magnetic heads now, just one. And so it was, really hard to sort of make all that happen. So it'll play back things with optical, with density tracks and area tracks, and basically every flavor. So how do we do it? Well, first of all, we decided early on it's largely software based, and we sort of followed the model of Tesla in terms of the features. So the hardware is done, but we're going to add features over time. As an example, something high on our list is that we want to add a feature where it will detect splices. So it'll be able to count splices. Part of the software in there now is condition reports. So when you do a scan, you get a condition report that shows you which frames are badly damaged. It tells you what the shrinkage is. It tells you, basic condition. And that's part of the scan, right? You get it when the scan is done. We wanted it to be open, and we wanted to be using standards. Open is a long topic, but basically we wanted it to be so that you could make stuff to yourself to work with a film. So I have an example here. This is what we call a trim tool. Those of you who work with film know that you open up a can, sometimes you have these little tiny pieces of film. Well, how do you scan those? Well, normally what you do is you splice them all together into a big piece of film. Well, that's labor intensive. It takes a lot of time to do that. And so what we did was we came up with this 3D printed scan tool. And what we do is you basically tape this down. There's no gate in the machine. And so you tape it down to the machine, and then you just pull your trims through. It goes through the camera sees it. Because it's a software-based machine, it's using software to figure out where the sprockets are, where the frames are. So you don't actually need a transport to do that. And part of that is being upgradable. We know that cameras will change over time. So the machine is designed, the camera in the machine is designed to be replaced. It uses the old tripod screw, remember those? So it has a standard plate on the bottom, and you put the plate for your camera on there, and we can switch cameras over time. So, if a new camera comes out with different resolution, or you want to do something different, you don't have to throw the whole thing away. You just replace part of it. So, how did we do it? And there's actually two parts of what we're doing, and it was more about changing our thinking as well as building machines, right? So it was more about thinking through the process. And what we basically decided to do is to work on two parts of the problem. The problem being, how do we digitize all of this film? And how do we do it like I just told you? And we decided to divide it into two different parts. One part is for low, medium, and unknown asset values, meaning that the stuff's in the can. You don't know what's in the can, and you don't want to spend a lot of money and a lot of time figuring it out. If it's really wonderful, that's fine. You can take it out and then do a high-resolution scan, a high-quality scan. But you don't need to spend a lot of money and a lot of labor to get the stuff out of the can. And that's been our problem. I mean, scanners have been around for more than 20 years. How come we still have all the stuff in the cans? How come all the stuff hasn't been digitized? And the reason is it's just too slow and too expensive. And so this part of the paradigm gets around that. So we wanted a fast, low-cost mass migration system while determining condition at the same time. We wanted it to be easy to use, and as part of the process, we wanted to identify the really good stuff. So the other side of the paradigm is, what do we do for things that are really, really important? Things that we know are high value. And remember, the film is deteriorating. So how are we going to capture all of that, as much detail as we possibly can, including what I call the character of the film? And we're going to do that by creating a data representation for film. We're going to get away from this idea of, oh gee, that film's pretty, or the picture looks okay to me, and we're going to a more scientific basis where we're actually going to create a data, what I call a data cube, well not what I call, but what's called a data cube, using multispectral imaging, and I'll explain that in a minute. And in order to do that, or what we did as part of that, is we have created really unprecedented and upgradable color capture, an upgradable and unprecedented quality capture, both in terms of the resolution and in terms of the amount of color. So what do I mean by that? Well, we're talking about 1 gigapixel, new term, not megapixel, 1 gigapixel per frame, per film frame that we're scanning, and we're talking about 160 bits of color. So I'm going to explain that in a minute. So we have these two different, yeah, it's crazy. So I know it's crazy. So we have these two different sides. We have one, like, let's just get this stuff done, let's get it digitized, and let's do it as quickly and cheaply as possible. And the other is, for our really valuable masters, what are we going to do? You know, for those kinds of things, 4K doesn't do it. 8K marginally does it. It's not about that. It's not just about resolution, it's about color depth. So, the filmic system, which is the mass migration system, can operate up to 4 of these EZ machines that you see in the other room at the same time. So there's EZ16 and EZ35. The EZ16 does 8mm and Super 8, and then the EZ35 does 35mm. Okay, they're 2 separate machines. Why didn't we do one machine? That's probably the most common question. Why don't we do one machine? And the reason is the cost of doing one machine that did everything was more expensive than having 2 machines that are specialized. And that's the reason for doing it that way. So, also by doing it this way, you'll notice that these chassis look basically identical. Okay, the chassis being the mechanical parts, that the mechanical machine that moves the film. When you look outside, you'll see that there's a Dell server inside, right, as part of the machine. And so the machine, the part that moves the film, that does the scanning, it's about 1.5 inches thick on the top. Okay, and the reason that we're doing one of the benefits of doing the same machine on the top for Rainbow as well as EZ16 and 35 is that we can buy more of them, of the same thing. And with factory type stuff, when you buy more, it gets cheaper. So right now the EZ16 is $30,000 US, and I think $29,000, and I think we're going to be able to get it cheaper over time. And the reason is because we're doing what's called economy of scale. So they're 2 different machines, but they share a lot of common features, and I'm not going to go through all of this, but the features of the 2 different platforms are shared, as well as somewhat with Rainbow. So by doing this, so you saw in the other picture that was a robot, right? And it had 4 tape decks, one on top of the other. Okay. Well, we've done the same thing with film, but instead of having one on top of the other with a robot, we're able to control 4 machines with 1 operator. So you can have 4 things migrating at the same time. The only way we can do that is by putting the intelligence in the scanner. Okay? And actually, I don't know if you've been in the other room, well, you were, those of you who were in the training, you know, once you start going, it doesn't need operator, and you don't need to do anything. Basically, you hit start and you walk away. It doesn't need you there. And the operator can be doing other things. And the operator, as I said, can be someone with minimal training. So the idea is that we want to be able to give people the information they need, because you don't want to be scanning this a bunch of times, particularly if it's low value. So there's 3 different kinds of scans that come out from the same scan. In other words, it's going to be scanned once, but you're going to get 3 different file types, or 3 different images in the files. And file types is a whole bunch of file types. It uses FFmpeg, so basically whatever you want to use, FFV, Matroska, you want to use ProRes, you want to use whatever, you can do that. It's all the open source stuff. So there's the full scan, which actually intentionally shows you a long strip of the film, because it's like a film bench. Those of you who've actually worked on those analog benches, it's like a light box and you can see the thing. Well, it's the same kind of thing, only it's digital. There's the inspection scan, which is basically close up on the frame. It shows you edge to edge, shows you the sprocket holes, shows you edge damage, shows you everything about it. And then there's the movie crop, and the movie crop is, you know, the movie. In addition, it gives you a condition report. And the condition report tells you what you want to know about the film. It's detailed enough so that you can look at it and go, oh, well, this film is pretty good, or this film is not so good. And it's color-coded, right? So it's kind of like a, you know, the sprocket holes, there's like a lot of shrinkage as an example, right? So it lets you know that. And it does it, you know, right now, how do you know which is, 5 minutes? Oh, I'm in trouble. Okay, I'm gonna move on. The rainbow is the system for high-value assets. This is a multispectral system, and some of you have come to me and said, we heard you talking about that in 2015, you know, where is that? Well, here it is. The rainbow, the idea behind the rainbow is to capture full spectrum. And we're not dealing with RGB anymore. We're dealing with the full spectrum. I'm going to show you that. We're not going to do cyan, yellow, and magenta, or RGB. What we're going to do is do full spectrum, which encompasses all of it. If you look at film sensitivity, those three humps are basically the sensitivity of a typical motion picture film. And you'll see where I have the arrows there that there are areas where the film is less sensitive, right? And what that means is effectively you have less data, where that in a digital sense, in the analog world, it has less sensitivity. But in the digital world, that equates to less data. And so what we want to do is get every bit of that and get it as much as possible. Those of you who've ever done color correction will know I'm wearing this shirt for a reason. Trying to get this shirt with an RGB image is really, really, really hard. Trying to get the right color is really, really hard. It's basic color science. It's not because the sensor isn't good or the camera isn't good. It's because it's the wrong color space. If we actually look at film, there's no pixels in film, right? It's an analog media type. We have layers. And if you actually look at a given pixel location or a different point, what you have is you have a curve, a spectral profile. And what we want to do is recapture that information. RGB doesn't do that because RGB is very limited in terms of where it is in terms of the width of the filters. And it gets much worse. What I just showed you was kind of a theoretical RGB filter. The real RGB filters are what I'm showing you on the left side of your screen. So this is from an actual camera, and every camera has a different response. But the problem here is that we have what are called Bayer filters. And Bayer filters filter, and that's how you get all of your RGB information. And the problem with that is that there's only 3 filters. So how are we doing it? Well, instead of having 3 light sources, we have 10. Okay? And each of the 10 light sources are narrow LEDs, and they're spread across the spectrum. And as you can see, there's one at around 425 nanometers, 450 nanometers, and so on up the spectrum. We have RGB represented as well, but the idea is that we're grabbing all of the spectral information that can be associated with a film. And if you actually plot that out, and you plot out their RGB, and you plot out film sensitivity, you'll see that you actually have very narrow filters, right? Created by the narrow bandwidth LEDs. This is very similar to audio. When I was a kid, we used to have a tone control, right? And so you turn bass, and the bass went up, but you couldn't hear the treble. You know, you couldn't hear the high frequencies. Or you turned up the treble, and then you couldn't hear the bass, right? That's kind of where we are right now. And then this thing called multi-band equalizer showed up. And then you could hear the high frequencies and also hear the bass drum, right? And that's what we have now. Everyone has it on our phone and our car and everything, right? And no one's ever done it in light before for scanning. And so that's what we've done. We basically built a multi-band, you can think of it as a multi-band equalizer for light. So what does that actually look like? On the left, you can see some of the circuitry for, this is actually the EZ circuitry, usually LEDs. When we started 5 years ago, the LEDs that we used, in order to use LEDs and not melt the film, we actually had to put the LEDs below the surface of the machine, below the chassis, and use mirrors and bounce the light up. There was so much heat that was generated. Now we're using LEDs for only 5 years. Now we're using LEDs, and the LEDs we're only using 20% of the power of the LEDs. There's been a huge change in the technology of LEDs, and it's an area of technology that's moving really, really quickly. Now with LEDs, we're able to buy LEDs that are very narrow in spectrum. And they're made by Philips. These are mass-produced, you know, in the millions, right? And we're able to select them, which means that we can choose spectral components that relate to, you know, marching up the spectrum. That's actually what it looks like. And as part of the design of the system, we have a photospectrometer built into the system. And so what that means is that when we illuminate, okay, I'm going to need another couple of minutes. When we illuminate it, we're actually able to make sure that we're getting what we would get. So, what kind of a camera are we using? We're using a camera with this kind of resolution. It's basically a 12K camera. Well, you can see what the resolutions are. These are all native resolutions. What that basically gives us is it's a 12K, each image is a 12K image. It's a medium format large sensor, so it's not a small regular 35 millimeter sensor. It's like a Hasselblad, for those of you who know what that is. It's 102 megapixels per exposure per channel. So we're doing 10 exposures for each motion picture frame. So we're shooting each frame with a different color LED, okay? And we're doing it 10 times before we move to the next frame. This is not real time. This is slow, really slow. This is the size of the sensor compared to regular 35 millimeter sensors. A bigger sensor means more light and more accurate information. Lenses are really important. Usually scanner manufacturers don't talk about lenses much, but lenses are really, really important. So what do you end up with? You end up, the original 35 millimeter film frame, you end up with 10 individual frames. Each frame has each file, has 102 megapixels and 16 bits of black and white information, or we'll say monochrome information, which represents the information from that one exposure to the LED. So, what does it look like? This is actually the CAD/CAM drawing. You can actually see the chassis, and if you go inside and look at the EZ, you'll see that it's the same exact chassis. The camera is on your right. On your left are the illuminators. There's an array of 9 illuminators. Each illuminator has 10 LEDs in it of the different color space. Looking from on top, this is a ray trace simulation of getting the light to the camera. And you can actually see how the light hits the diffuser. This is looking from the film, looking at the illuminators. And that's what the rainbow is. So, I'm done.
So let's move on. Next we have Bertrand LAVEDRINE, who is he is not a stranger to Sapava, has spoken at many Sapavas in the past, giving workshops, etc. He's a professor at the Muséum National d'Histoire Naturelle and a scientist at the Centre de Recherche sur la Conservation in Paris, France. And he was appointed to Judith Proska Distinguished Visiting Professor in Conservation and Technical Studies at New York University. He has participated in various international training programs funded by the Mellon Foundation, Getty Conservation Institute, and ICROM, and research projects funded by the European Commission. So take it away, Bertrand.
All right, hello everyone. It's really a pleasure to be here today and to be back at SEAPAVA conference in person in Thailand. It has been too long since the meeting in Bangkok in 2018, and I would like to thank the organizer for giving me the opportunity to present this project. And this work has been carried out in the framework of a European collaboration between various countries, France, UK, Germany, Portugal, Poland, Bulgaria, Spain, Italy, Austria, Ireland, and Czech Republic. And the European Commission had funded this joint research project entitled Mnemosyne, and it was a 4-year research project dedicated to the preservation of film heritage and devoted to alternative storage techniques. As you know, the international standards recommendation for archiving cellulose triacetate films over a long period of times, and I mean more than 100 years, is to store them in cold room at temperature below 10 degrees Celsius or even below 0 Celsius. And this method has proved to be very efficient for the preservation of photographic and movie film heritage, and has allowed to extend the life expectancy of acetate films. However, today it raises question about its carbon footprint, because in most cases the operation of the cold storage facility requires fossil energy, and the running costs are getting higher too, nor affordable for archival institutions. So it has become necessary to find compromises or greener strategies, and we therefore looked for introducing more passive strategy solution for the conservation of movie film heritage. So when I began working in this field, the field of photograph preservation in the 1980s, more hair, it seemed that the problem of preserving motion picture film was solved with the use of cellulose acetate base instead of the flammable cellulose nitrate base. In 1981, Eastman Kodak company announced a life expectancy of 300 years for cellulose acetate films. However, in some countries with tropical climates, archivists were already seeing, or I should say rather smelling, the decomposition of cellulose acetate, what our community will call later the vinegar syndrome. And these early warnings were confirmed by Michel Age in a series of scientific papers in the late 1980s. And in the following years, a growing number of heritage institutions reported the occurrence of vinegar syndrome in their collection. And so finally, the Image Permanence Institute demonstrated through an extensive studies the short life expectancy of cellulose triacetate. Also, it was not flammable. Its lifespan could be less than that of cellulose nitrate film. And these studies conducted by Peter Adelstein and Jean-Louis Bigourdon highlighted the impact of temperature and humidity on degradation and the orthocatalysis phenomenon. That is to say that the acetic acid produced during the acetate base hydrolysis accelerates the degradation process. And then several options were possible to slow down film degradation. And I say to slow down. In addition to storing the film in a cold storage environment, as I mentioned before, another strategy was to trap acids emitted by the film during its decay. So in 1993, the Kodak company introduced the use of zeolites, known as molecular sieves. These zeolites are very porous aluminous silicates which can trap acid molecules in their pores. So Kodak filed a patent in 1993, and these zeolites were made available, shaped in beads in Tyvek pouch, to put around the film reel in the can. And Kodak company recommend to use around 37 grams for 300 meter of 35 millimeter film to be renewed every 2 years for storage at room temperature. A few years later, the Fujifilm company introduced on the market its own zeolite, an aluminum hydroxide, under the name of Keepwell, and they were packaged in as patches to be placed on the surface of the reel. I am not sure that the Fujifilm company still produce Keepwell, but similar products are marketed today by the Japanese company we heard this morning, Imagica, either in the form of patches or in the form of small bags filled with zeolite. And those zeolites can absorb some acetic acid. However, it absorbs more moisture, more water than acetic acid. And it is effective, but the improvement in preservation is mainly due to the absorption of moisture rather than the removal of acetic acid. Then within the framework of this Nemozyme project, we try to develop and test other adsorbents more efficient and more selective for acetic acid capture. And the first step of this research was to determine what are the VOC emitted by a film and their emission rates, because it was important to identify any VOC that might compete with acetic acid in a scavenging process, but it was also necessary to find out whether these other volatile compounds emitted by the acetate base could interfere with a specific sensor for acetic acid that was planned to be developed in this project. So to identify the VOC emitted by a film and their quantity, we use a relatively recent method of analysis called PTRMS, acronym for Proton Transfer Reaction Mass Spectrometry. I'm sorry, after lunch, such a heavy name, but this technique is really incredible. It allows for real-time quantitative and qualitative assessment of VOC present at ultra-trace levels from part per trillion, ppt, to part per billion, and it is highly sensitive. As an example, if you approach a bottle, it may tell you what is inside without opening it. So it's a very, very sensitive method, not for all compounds, but for many VOCs. And for our test, the French film archives provide us with 41 cellulose acetate film, 35 millimeters, in black and white or color, and of different brands, different degradation level, and dating from the 1970s to the 1990s. To be analyzed, we put the film in a Teflon chamber, that the air is sucked in from this chamber and introduced in the machine, in the PTRMS, when there are chemical products are analyzed and they are combined with protons, and the mass spectrometer helps to identify them. And we identify over 121 different VOCs emitted from the cellulose acetate movie film. And those emissions were stable over more than 10 minutes. And those compounds are either degradation product, residue, or additive from the movie film, from the base, but also from the image layer. Among this huge variety of products, acetic acid, acetaldehyde, acetone, butanol, dimethylformamide, formic acid, methanol, propanoic acid are the most commonly found. However, acetic acid is not always the most abundant VOC in the film can. We analyzed, in 3 cans we found mainly dimethylformamide, in 6 other mainly butanol, in 2 other mainly acetaldehyde, and for 2 mainly formic acid. So the emission rates reach more than 10 ppb of acetic acid or dimethylformamide per second. So those results were very interesting, since we did not expect such a variety of compounds in film cans and such emission rates. Thus, the compounds to be neutralized were mainly acetic acid and some formic or propanoic acid. The other compounds should not speed up the film degradation, but may pose health and safety issues. To trap acetic acid and other acids, we tested a new kind of porous materials, the metal organic framework, or MOFs, that have been introduced around 20 years ago. MOFs are crystallized porous solids synthesized in the laboratory by linking metal ions with organic molecules, and there is a very large number of possible combinations of linkers and metals that leads to a wide range of structures with tunable pore size and polarity suitable for the selective and absorption of gases, and at present over 90,000 MOF has been synthesized. It is hoped to use them for CO2 trapping, but they have proven to be interesting in many other fields such as air quality, gas separation, and biomedicine as drug delivery. In our project, several of these compounds were synthesized and evaluated for their efficiency to trap acetic acid in film cans. And thanks to our partners, in situ specialized in porous materials, we selected a special MOF named 1100 that meet our expectation. And this compound has many advantages. It is cheap, it can be produced by a green synthesis at room temperature in water, and acetic acid absorbs strongly to metal site, and there is little risk of release. Laboratory tests had shown that this 1100 MOF outperforms zeolite and other porous materials, not only for acetic acid, but for other VOCs. Thus, we decided to test this MOF in film archives. We filled Tyvek bags with 150 grams of 1100, and these bags were sent to film archives, the Deutsches Film Institute, the Austrian Academy of Science, and the Institute of Valencia de Cultura in Spain. So the films selected for this test had an acidity level around 1.0 to 1.5 on the ADE-strip scale. That is to say, an acetic acid level range to 1 to 5 ppm. Those MOF bags were inserted into a specially designed box lid manufactured by Acumplast company. There were also a space on the side that allows sensor to be placed near the film in order to monitor continuously online the acetic acid concentration in the film can. This sensor was developed by our partner, Biosensor, in the framework of the project. I present here the test made in the film archives in Valencia on a black and white negative film with an optical sound entitled Un Militari Medio, dated 1959. And we measure the acetic acid concentration in the can. The average was around 2.2 ppm. Yeah. Right. So the average was around 2.2 ppm. Then we added the MOF, the lid containing the MOF bag, and the acid concentration dropped from 2.2 ppm to 0.3 ppm on average, and remained at that level for at least 1 month. And unfortunately, the delay due to the pandemic did not allow us to continue the experiment for longer periods, and then to determine when our absorbent would be saturated. However, according to the theoretical models that my colleagues Abi Mota from the University of Lisboa has established, it should stay efficient for a few years and significantly slow down the acetate degradation process. Keeping 10 years a fresh 2 kilo cellulose acetate film at 22 degrees at 50% relative humidity with 100 grams of MOF 1100 produce the same benefit as keeping it at 5 degrees Celsius for 10 years without MOF. And if the film is already degraded at a strip ranking of 1, the amount of MOF should be double. That is to say, having 200 grams of MOF in the film can at 22 degrees Celsius will produce the same benefit as storing at 5 degrees Celsius. And however, there was still one aspect that we wanted to improve, the shaping of MOF. MOF is produced as a powder, And the usual shaping is in the form of granules or beads that are not very convenient to handle and to use in film archives. And I therefore propose an alternative solution which consists of incorporating these MOFs powder into sheets of paper. So paper sheets are easy to store, to handle, to cut to box size. However, introducing a large quantity of a filler in paper, such as MOF, is not easy because beyond a certain limit, the paper becomes very brittle and is not easy to handle. So I therefore mixed the long cellulose fibers used to produce papers with nanocellulose, microfibrillated cellulose dispersed, and this helped to create cohesion between the MOF particles and ensure a better cohesion of all the components of the composite. So thus it was possible to produce a membrane with more than 70% of adsorbent, of MOF, which remained quite flexible. So in collaboration with the conservator of the National Archive, we produce 20 by 30 centimeter sheets of MOF paper. And our students, Pierre Tignol, tested, characterized, and optimized the properties of these composite materials. This shaping does not modify the absorbing property of the MOF, which keeps all its characteristics. Finally, to ensure that this material would not damage the motion picture film or any photographic material, we apply the photographic activity test. And our MOF paper passed this photographic activity test. So far, these MOF paper sheets gave promising results for trapping irreversibly the organic acid, and it appears to be a very promising way to extend the life expectancy of acetate movie film in the context of sustainability. However, it may not extend the life expectancy of dyes in color chromogenic film or nitrate film. These MOF membranes prototypes can find other applications than cellulose acetate film preservation, in particular to protect archival documents or acid-sensitive museum objects, and a patent has been filed, and we are currently looking for industrial partners to bring this product to the market. To conclude, I would like to thank the European Commission for supporting this Mnemosyne project and all the project partners, my colleague of the Institute of Porous Materials in Paris, the Research Center on Conservation in Paris, the University of Lisbon, the Institute Valencia de Cultura, the Austrian Academy of Science, and Nadja Valoskiewicz, the French National Archives, the French Film Archives, Biosensor, MPLAS, and thank you for your attention.
Yeah. Now I believe we have a Zoom presentation, is that correct? From Peter SCHALLAUER, who is an R&D and product coordinator for the audiovisual solutions in the research area.
Hello.
He's been working with Joanneum as a scientific and development coordinator since 1995 and has created a wide range of digital video and movie technologies and systems, including the DAMSmart film restoration and audio, which many of you are familiar with, automatic film and video content analysis, content description, efficient digitization documentation, etc., etc. So we're going to hear a little bit about quality control, a topic that, again, we should all be very interested in. So take it away.
Hello, good afternoon. My name is Peter SCHALLAUER from Joanneum Research, located in Austria, Central Europe. Today I will talk to you about quality control experiences and 3 large projects we have been involved with by providing to film archives quality control solution and helping them for setting up an appropriate workflow for ensuring the digitization quality. Today I will talk first about the film media itself, what kind of properties it has and why it is quite demanding concerning digitization and quality control. Then I will give you an overview on the 3 projects from different archives. Then I will talk a bit more in detail about how the quality control process was implemented for image and sound quality control, which is the main focus today. There is another kind of quality control, which is about the file formats, the encoding formats, which are also relevant, but which will not be part of the talk today. Then I will give you an overview about what kind of issues has been found and in which quantities. And finally, I'll give you some feedback also from the archives who did the quality control, so what lessons they learned and what operational experiences they made in the recent years. When looking to film as a media, which is there for almost 150 years, at the first glance you could say, yes, it has not changed so much, but actually when you're looking a bit closer, there are many aspects which have changed and are changing over time. So there have been used many different film stocks, different sizes of these stocks formats. In general, all of them have a medium to high spatial resolution, even compared to nowadays productions. Especially the densitometric resolution, so the luminance resolution is very high with film, which causes also some challenges in digitization. Color fading can happen over time. When looking to the exposure and to the light, which is digitized, actually for each individual film, the light which is coming through the film depends on the original analog film exposure, on the original analog film development, and on the scanner exposure during digitization. So there are many influences over time. Film is specific as there is a mechanical transport, so the perforation is used for the transport but also for synchronization. There have been used different splicing methods and qualities, so splices can be quite ugly over time. Image and sound is often separated in different systems. There have been different sound formats, and of course there have been over the last 150 years different storage conditions, which is probably especially valid in Southeast Asia and the Pacific region where humidity and temperature is quite high. So when thinking about all these aspects, it's important to say that film needs really specific attention during digitization in order to not lose image and sound quality of the original high quality of film as it was. The 3 film digitization projects I'm talking about today are the ones from Indiana University, from Bayerischer Rundfunk, and from Israeli Public Broadcast Corporation. They have a digitization volume which is in the range between 20 and 50,000 reels, so quite large size. They started 2017, 18 and 19. The one at Indiana University is already finished. The Bayerischer Rundfunk one will last until 2028, and Israeli Public Broadcast Corporation is also almost finished. Concerning the different film formats and stocks, it can be said that Indiana University is of course a university archive which has different formats and stocks, many different ones, but mainly 8 and 16mm, but also 35mm. Then Bayerischer Rundfunk is mainly a 16mm TV film archive, but they have also some 35mm, and Israeli Public Broadcast Corporation has mainly 60mm TV film, news film. Yeah, one aspect which is maybe relevant to mention is that at Indiana University and Bayerischer Rundfunk, they planned and introduced the quality control of the digitization in the process, so it was planned and done, and it happens soon after the digitization, so usually between days and maybe 1 or 2 weeks. The situation is different for IPPC, where they encountered issues after 1.5 years of operation of digitization, major issues, and there is happening now a kind of retrospective quality control in order to figure out what really the bad films and digitizations are in order to go back to the service provider. These three archives are using one workflow, so the same workflow for doing the image and sound quality control. As you can see it here in the graphics, it is starting with the film scanning and mastering, which is done by a service provider. In all cases, the only differences are they are using 1 or 2 scanners at the same time. They are operating in 1 or 2 shifts and they're using different tools. But in all cases, the result are audiovisual files which are transferred to the archive. The archive is doing the quality control, and it's doing that in a 2-step approach. First, the files provided by the service provider are analyzed automatically in regard to specific film scanning issues which might be there, and is preparing information in an automated way for a second step, which allows for interactive verification and finally making a decision about whether the quality is acceptable or not. If a file, the quality is not acceptable, it's rejected, a PDF report goes back to the film scanning service provider. He's doing remastering or rescanning and remastering, and the same film or the media of the same film are going through the same QC process. When the files are accepted, then the whole process is documented, so the quality reports, XML reports, PDF reports are becoming part of the archival package, and they can be used immediately also later on for driving digital restoration activities, if that is desired. And here you can see how the QC stations and interactive stations are typically set up. In this case, 2 stations, and each individual station has 1 monitor for showing all the analysis results and allowing the operator to navigate through these detections found in the automatic step. And there is another monitor which allows to play back in a time synchronized way the media in full screen. So that's an efficient setup for doing QC for film scanning. Within the used QC software, there are different functions for finding specific film scanning issues. So specialized functions like finding clipping or crushing situations, like finding jumping framing errors, jumping frames, finding unsteadiness or out of focus situations. Finding also bad splices, bad cropping, crookedness, and also wrong playback speed and some audio deficiencies which might be there. In the interactive verification, there is a user interface which gives an operator the overview over time of the different quality aspects, like how shaky the image is, how much dust is inside, and so on. And it allows the operator to verify detections which are coming from the automatic analysis step. It allows the operator also to annotate manually if an operator comes across something which has not been detected in the automated step. It allows also the operator to check the content, whether the content is correct, times codes are good, whether the image and sound is there. And it allows also to document the QC decision process in a specific field. Out of that tool, different reports can be created. First, a machine-readable XML report. Second, a human-readable PDF report, which is especially important for feedback for the service providers for scanning. And third, a restoration report can also be created for later on restoration use. Within 2 of the 3 projects, we were able to do some statistical analysis of the issues found. So the basis for the statistical analysis you see here is that an QC operator is in the user interface is verifying a specific detection, like there is a jumping frame or there is a situation where clipping is happening, and is actually giving the information to the system whether this is real an issue or it is not one. Yeah. So it is so the statistics you see here is based on verified, human verified information. First, here we see the results for the image and sound QC at Indiana University. What you see here at the bottom are the different kind of defects they came across, and on the vertical axis you see the number of defects, the average number of defects per file of a specific type they came across and verified. So what you see here is, for example, in Indiana, there were many situations where there is dirt on the film, quite many framing errors or jumping pictures out of perforation problems, quite many issues because of gumboot clipping, and so on. So the red bars indicate the number of defects within the files which needed to be rejected at the end to the service provider. And the green bars are showing the numbers of defects contained in the files which are going back to the archive. And as you can see here, in the files which needed to be rejected, there was a much higher, 6 times higher amount of issues as in the files which are going back, which are finally accepted and going to the archive. Important to see here is also if a file is rejected in the QC, it goes back to the service provider, and this goes again through the QC process. So the newly mastered or newly scanned and mastered file is going again through the QC process and is becoming part of that statistics we also see here. So within all the accepted files at the end, they contain also the rescans, also the remasterings, which also explains that not everything can be solved by rescanning and remastering, but many things, issues in film scanning can be solved, can be made better if you detect them and if you remaster or rescan. And the difference actually is 6 times less issues in the files which went to the archive finally than the ones which needed to be rejected to the service providers. And this shows on the one side issues can be detected, but they can also to a very large extent be avoided. So what you see is here are the statistical results from the Israeli Public Broadcast Corporation. Here we see in this graph the red bars, files again rejected and defects in rejected files. Here we see that this one specific defect, macro blocking, was very heavy, often occurring in those files, and beside the other ones which are also happening in other projects like the framing error, permanence crushing, luma error, and so on. The reason for this is actually that an encoding issue caused severe macro blocking problems, which we could detect in the system because they were visually there, strong macro blocking in every iframe. So this the QC software could detect them easily, even if it is not a system which detects standards compliance issues. But as they were visually visible, it was detected also. And again, here in the Israeli Public Broadcast Corporation project, the files which went to the archive at the end had more than 6 times less issues than the files which we needed to be rejected to the service provider. Maybe to mention here in the IPPC, there was also done not a qualitative documentation of additional issues like splice bumps, which happened there often, and also AV sync errors and scanning unsteadiness issues, but they are not part of the statistics we see here at the top. besides detecting specific audiovisual issues and the quantities of it, it might be of interest where these issues have been originated from. And this slide is an attempt to give you an overview of these several years of operation and findings in these projects. And we have seen at least 4 areas where most of the issues are coming from. One area is really the light adjustment on the scanner. This causes over and underexposure situations, wrong contrast, wrong black-white levels. This is especially important or crucial when a production format is used with low densitometric resolution. It is less crucial if a higher quality format is used, but still it's a question of adjusting the scanner and the light of the scanner. It is also more crucial if you're doing one light scans, so one light from beginning to the end of the film. And this is especially valid if you have merged films. So some digitizations, newsreels are merged together in order to be more efficient in digitization, but of course they don't have the same properties in the film stock. This can cause also light adjustment problems. Yeah. A second area for issues is the film transportation itself. This is either caused by the physical condition of the film itself, or it is caused by the adjustment of the scanner. So the human who is adjusting the scanner for a specific film. This causes unsteadiness or can cause unsteadiness, framing errors, bad cropping, bad splices, splice bumps. A third area of origin of issues is coming from the equipment itself. So when the film cleaner is broken, that's a major issue which happened. Wet gates are always not always working. Image processing can fail within the scanning devices, which causes black frames, grouped frames, or frozen frames. Also sound processing can fail, causing silence or interstitial errors or wrong audio levels. A fourth area which can cause troubles is the mastering after scanning. Here you can produce audiovisual asynchronicity. Color correction can be done not perfectly, and also encoding issues are coming in, as we saw before with the micro-blocking stuff. In these 3 projects, various operational experiences has been made, and of course lessons learned. And I try to summarize them in that slide here. The first one is when to do quality control, and the clear answer is as early as possible after scanning. The reason for this is if you have a situation where a systematic issue happened, for example, a film cleaner is broken, from that point on all the films are not cleaned anymore, and if you encounter that in QC, if you have a backlog in QC, for example, for 2 or 3 weeks, and you would encounter that 2 or 3 weeks later, you have to re-clean, re-scan, and re-QC all the items from in between. So if you want to avoid unnecessary work, do the QC as early as possible after scanning. Then there are specific times in a QC or in a digitization project where QC needs specific attention. This is in times where personnel is changing, whichever personnel it is in the whole workflow, scanning, mastering, QC itself. When the film stock is changing, so it depends a lot on the archive you have, but when film stock is changing, also properties are changing, and of course when hardware and software is changing, hardware and software updates can bring also troubles in, not just solve troubles. Then, as a general observation, what was surprising in these 3 projects is that the files or the scans which needed to be rejected and the rate of these files can be quite high, as we see from the Indiana University and also from the IPC project. can be in the range of 25%. In this IPPC project, it was even higher with the special case of encoding issues, 46%. So surprisingly high. So what you see as a consequence out of that is plan also for a rejection workflow. So don't await that nothing needs to go back. Plan for it. And of course, very important, in the IPPC project, a retrospective QC has been done. This is of course not was the only option in this project, but the lesson learned from it to QC as early as you're starting your digitization activities, not a half a year or a year later. You can avoid a lot of time and trouble with the service provider if you're doing QC in line with the scanning. And at the end, it makes also the life of the archive and the service provider more happy, as you come 1.5 years later and have to tell the service provider that he has to redo a lot and make new negotiations for that. On the positive side, of course, QC brings a lot, so it can detect issues, and it can also, if you're doing QC, like in these 3 projects, and you're doing then, if you found issues and you're doing rescanning or remastering, you can really reduce the number of audiovisual issues significantly. In these 2 projects at IPPC and Indiana, it was by a factor of 6, so I think that's significant. And there is the other project from Bayerischer Rundfunk, where we see also that the rejection rate of the files went down. In the first year, they had a rejection rate of 16%. 16% of the scanned films went back to the service provider, and this went down to 10% in the second year and 5% in the third year. So if you're doing a consequent quality control and having a good discussion basis with your service provider in solving issues and making things better, the Bayerischer Rundfunk project is a good example of how you can bring down the rejection rate over time, which makes the archive but also the service provider more happy. Yeah, some overall conclusions. We have seen film. Film is on the one side a high quality analog media, but on the other side it has some specific properties which needs attention during digitization. It is possible today, and very well possible, to produce a digital preservation master today if you have a suitable QC process in place. And I think we could, and the archives are showing that, 3 archives. Semi-automated QC is possible also today, like in these projects, with reasonable cost. We did not speak about cost so far, but just to give you an idea, the effort for doing quality control is a fraction of the effort which is needed for doing the film preparation for these projects. So it is additional cost, but it is probably worth to do it, as if you do it good and well the first time, you don't need to redo and rescan things later on. Yeah, we have seen that large film digitization projects like these are underway, and they have been also finished successfully. And I'm happy to share experiences from these projects for potentially new projects, whether they are small or if they are large, whether they are in-house or outsourced. I think all of these projects can gain from experiences made, and I hope they are used. Yeah, I would like to thank especially the persons who are responsible at the archives for the quality control. This is Sonja Raffler at Bayerischer Rundfunk. This is Billy Siegel at the Israeli Public Broadcasting Corporation. And this is Daryl Myers from Indiana University. And of course, I would like to thank you for your attention.
So I think, do we have any questions? I have a few comments, but I'd like to open the floor first.
Thank you, all three of you. That was a really great afternoon session. My question is for Bertrand. You said that MOF paper does not work for chromogenic film. Can you expand on it? Thank you.
Yes, thank you for your question. It's allowed me to make some clarification. This MOF paper has been made to trap acetic acid to slow down the degradation of the base. But it will not slow down much the degradation of the dye itself. That's a different, yeah. So it may help because acetic acid may speed up the degradation of the dye, but it's not made for. Neither nitrate. We are working on a system to trap off-gassing from nitrate film, but this one is just made for acetic acids and other organic acids.
Thank you for the presentation. I have a question for Bertrand. Your presentation was very fascinating. I have a question. I'm sorry if I misunderstood your concept, but is that nemosine film is it already being used at archives, or what's your next plan with this project?
Well, that's a good question. You know, it's a problem of the European fundings. They give a lot of money for research and then it's over. so then you are your product, your prototype, and you have to find a market. And that's what we are at this stage. We made nice boxes for testing, we had a product, and actually we are looking for some company or to have a partnership with a company to put on the market the MOF paper, because we find it's a very convenient way to use it in library archive or movie film archive. You know, it can be used in many, because you have organic acids, acidic acids in paper degradation, in natural history collections. And the good thing with this paper, if we can add different type of MOF to trap different kind of product, it's very versatile. We can adjust the content. So we find it could be very useful, but you know, when it's a niche market, that's what the industry say. Oh, it's a niche market, we don't make enough profit. The good thing with this product is it's not only for archive, but it may be interesting for people in houses, because it can help to purify the air. So we are in contact with some company who have some interest, but you know, it's always a long, at the European level, we talk about TRL, technologically readiness level, and to be on the market, it has to be at the TRL of 9, we have a TRL of 6, so it means there is a lot of steps to go through to put a product on the market, but that's the wish and that's the goal of our consortium of scientists, me and others.
Okay, I have more questions, but I'll ask you later. Thank you.
Thank you. I have a question for Jim. Yeah, I think it's a fascinating. I mean, using multispectral imaging, hyperspectral imaging, we use it a lot in the field of art, but it's generate a lot of data, very heavy. And I was wondering, when you do it for a film, why do you need to do it for all the film? Why don't you make the first? Because they're same dyes. So you can just take the spectral characteristic of the dyes for 2 frames, and then you keep it in your system, and you can extrapolate with normal scanning. I'm not sure I'm clear enough.
Yeah, I don't know. Well, we're capturing every frame, right?
Yeah.
So the idea is we want to capture all the picture data. We want to capture all of it through the whole thing. So we don't want to take the shortcuts that our entire field is taken from the very beginning of filmmaking. And so, you know, data's cheap.
It's cheap. Yeah, but that's every files.
Every file.
Yeah, big
okay,
file.
so, it's 250 terabytes
Yeah.
for 90-minute film. Yeah, well, that's okay. So So my cell phone has, okay, so I was in the computer animation business.
Yeah.
And we went out of business in 1990. We had almost 40 employees. And when we went out of business, the entire company had almost 1 gigabyte of storage. Okay, 1990, right? Now my cell phone has 250 gigabytes and it costs like $600, you know? So, the cost of storage, you know, the raw cost of storage, and the cost of storage really is more complex. You know, the servers and all of the other stuff. I think the time has come to just get a data-rich environment. And so I'm going to leave it to the future that if they want to thin it out, they can. But when you have all of the data, you can do things like fast Fourier transforms. You can do all sorts of other analysis that if you start pulling it out, you lose it. We spent a lot of time losing data. I'd rather not.
Yeah, that was my second question, because with this feature, you probably can know what kind of dye it is, what kind of brand, and what is the level of degradation of the acetate base, not based on shrinkage, but based on the chemical degradation.
Yeah, you can know whether the director, the editor was smoking, right? Or whether you had a peanut butter and jelly sandwich when he was editing, or whether. I have a lot of data.
Sorry, you're wondering what you're saying, but we're just saying that we've got that analysis happening, so we can have an MOF paper to go with that analysis. So we might have to work together.
What I'm going to say is that it's about coffee time, but one of the last presenter is not going to be presenting by Zoom. He's not unable to, so we will have like 20 minutes plus at the end, and I would like to invite Josh and Bertrand and Jim at the end to take more questions and comments. Okay, welcome back. Hopefully you've had a nice, refreshing break. We are ready to have the next talk from Joshua from Archives New Zealand. Many of you know Joshua, of course. And he currently works as the Digital Preservation Analyst at Archives New Zealand. His responsibility is to ensure that all necessary processes are in place to maintain the integrity of the government digital archives. And he's been involved in the Utaina project, Utaina, in New Zealand, some of you may have heard about. And he's a strong advocate for open source tools, and he's co-facilitated training courses on a variety of topics, both in person, at Sapava, and online. And he's gonna, I'm sure, tell us about many interesting things in the lossless compression world, and how we could use his expertise in our own work. So take it away, Joshua.
Hi, thanks Joshua for introducing me. Yes, so I'm from Archives New Zealand. We are the National Archives of New Zealand, and we hold the government records of Aotearoa, New Zealand. We don't collect, we receive transfers from public offices. We are basically operating on a legal framework, Public Records Act. What this means is that if you are a public office and once the information that you have created has finished its business purpose, you would have to dispose of it, and disposal means either destroying it or transfer to archives, and that's how we get most or all of our holdings. So we don't have a legal framework to actively collect anything, but there's enough work to be done. So, as you can see here, this is a digital repository, and we have also a digital one, and we call it the Government Digital Archive. In it, one of the major components is a digital preservation system. We use Rosetta by a company called Ex Libris, and a good 10 years ago we decided that, hey, National Library in New Zealand they are also doing digital preservation, we are also doing digital preservation. Let's work together and let's just use the system. And so since then, we have been sharing this digital preservation system. It has like a consortia function, so we don't see each other's content, and we have our own like little space, but the back end and the other things that's supporting the whole operation is one instance. So, digital preservation, when I saw this year's theme, I was like thinking, digital preservation is essentially thinking about digital sustainability, right? We like to say that in the digital preservation, it is an active and continuous process, and we talk about how it is financial staffing, and recently we also included the discussion on environmental sustainability. So I was thinking, yeah, it's actually equivalent, I would say. And some of the quotes or sentences that has used to describe digital preservation or digital sustainability are, in particularly, I was thinking, building an infrastructure and approach that is flexible with an emphasis on interoperability, continued maintenance, and confirmed development. And the focus today, because I'm talking about lossless compression, is interoperability, right? And how it is actually going to reduce environmental impact. And the third one, on the screen you can see that it actually says that if we are going to think about digital sustainability, we have to take into account the broader context in which our work sits, the wider responsibilities that we have, which includes environment. So this leads me to, this is an NFSA promotional slide in a way, not my own institution, but this deadline 2025 has quite a large influence on this massive project that we are doing right now. So Utaina is the project that we're currently in flight, and what we are trying to do is mass digitization of all the magnetic media that is owned by Crown, so government records essentially. All of the magnetic media that we know exists would naturally fall in scope of this project. So it is an ambitious project. It's one of the largest digitization project that New Zealand has ever done, and I think it's one of the largest that I know of. The total number of items is about actually 500,000 items, because we work with 3 major agencies: National Library, Archives New Zealand, and Ngā Taonga Sound and Vision. But because I'm from Archives New Zealand and we work with National Library more, so my analysis and what I'm going to talk about is more, I have an extra 1 in this slide, sorry, it's 150,000, not 1 million. I'm only going to talk about the 150,000 items that we have between National Library and Archives New Zealand that we have estimated that we have. And it's about 155,000 hours of video plus audio, and we estimate it will generate about 1.5 petabyte at the end of the digitization project. So it is quite a huge amount for us. And breaking it down, so there's National Library and Archives New Zealand, and we are talking about just Archives New Zealand. We have about 12,000 items of audio and video, and actually about only 3,800 items that's video, and that works out to be about 6,000 over hours that we have to digitize. And that works out to be about 700 terabytes, so from 1.5 petabytes, Archives New Zealand has a share of about 700 terabytes. And this calculation is done using the format that we were using back then, which is V210 MOV uncompressed, a very common uncompressed format that a lot of people, institutions would have used or are using. It generates about 100 gigabyte per hour of footage. So this gives us about 700 terabytes of estimating storage that we would have to handle. So in this graph, this is the kind of like storage size that we have in our collection for Government Digital Archive, GDA. So you can see that we started about like 2010, and until 2021, 2022, we are about 300 terabytes. So an increase of 700 terabytes is more than doubling what we're going to have. And this is going to happen in less than 3 years. As you can see, the graph just went crazy. So the amount of data that we are supposed to handle is a lot, and it's unprecedented, and we need something. We need to figure out how to reduce it or do something smarter about the data that we're going to have. And so naturally, we look at lossless compression. And at the time when we were looking at this FLV1 codec is gaining traction. There's a lot of conversation and a lot of activity in this space where they are about FFV1, the codec. And we were thinking, okay, maybe we should give it a look, right? What can we gain if we're going to change our preservation master format from an uncompressed to lossless compression? And it turns out, through our own testing, we get a reduction of up to 50% of the file size. And that's a huge, I would say, confidence boost in the kind of solution that we're looking at. And of course, 50% reduction in file sizes means 50% reduction in storage space, and it's also a reduction in the transfer bandwidth requirement, transferring the files in between places for different processes, and also reduction in the processing time. Fixity, validation, QC, everything is going to be less because the file size is smaller. Makes sense? But there are also a bunch of other considerations, like what do we want and what are the things that we are looking at when we are choosing to change the preservation master format. And I'm not going to talk about every single one of these, but particularly digital storage, bandwidth, and processing time were the three things that we saw a major benefit from going with this format. And playback complexity is how easy is it for us to playback. Timecode support, some of our materials has timecode, would you be able to handle it? Closed captions or subtitles, would you be able to handle it? Reversibility, is it truly lossless? Can be proven. Adoption by other institutions, other people using this, how are they using it? Format specification and standardization, is this format standardized? And environmental impact, which is the focus of today's talk. And of course, vendors' ability to actually handle the format. We can ask for a format, but if the vendor that we are asking to help us digitize cannot handle the format, we can't proceed. So, to understand what is this lossless compression FFV1 codec, we look into what it is. And of course, the information that I'm presenting right now is more up to date than when we were considering it, but when we were trying to prove to our leadership team like lossless compression, we thought we came up with this analogy of it being like zip. So zip file, I guess most of us are quite familiar with it. It's essentially you put a bunch of files, you zip it up, the size might reduce, but when you open it up again, you expect everything to be the same. You don't expect things to be different. So that sort of helped us to explain to management that lossless compression is the general concept is as such. And then we have to also kind of explain what is the FFV1 codec. And it is an open file format. It is lossless intra-frame video coding format. Basically, it is compressing within the frame. And it is also part of the FFmpeg open source library libAV codec since 2003. What this means is that it is not something that is just newly created. It has been part of an open source library that has been used in a lot of applications since 2003. And it uses an algorithm, two algorithms actually, is either variable length or arithmetic coding, and to basically reduce the entropy in the format. So basically it's trying to reduce the size, and these are the algorithms to use that is in the format to try to reduce it. And the most important thing is that it's without patent. Right? So it is open source, it's available, and it's without patent. And in 2021 August, the Internet Engineering Task Force has approved and issued this standardization RFC 9043. And what this means is that it is now a standard. Right? It is not just a format that someone created in the garage. It is a standard that has gone through rigorous review process and in the standardization body, Internet Engineering Task Force. And the group that's working on this is, they call themselves the SCHALLAUER Working Group, Codec and Encoding for Lossless Archiving and Real-Time Transmission, and it's actually chartered by IETF. So it looks good. FFV1, it looks decent, and we were thinking, okay, there's FFV1 as the format, and we need a wrapper, a container to wrap it around it. And the recommendation at that time was FFV1 MKV. MKV stands for Matryoshka, so it is the video container, and the name is derived from the Russian wooden doll, Matryoshka. And as the name suggests, it can hold an unlimited number of items, elements, video, audio, pictures, subtitles within it. So you can keep making it smaller and smaller, and it's all in one package. And it is based on EVML. It's a type of binary XML, and it is in widespread internet usage since 2002. It's not something new. In fact, a lot of us in Southeast Asia, in the region, are very familiar with MKV, or some of you know what it is. It is the format that originally was designed for streaming, and it is widely used. And because it is also part of upstream FFmpeg support and direct show and all the other playback libraries, a lot of the platform out there like Xbox, PlayStation and Windows 10 is natively able to playback something that is read with MKV. And that is a big, I guess, benefit of using a container like this. And most importantly, for digital preservation, each of its element, whether it's a video, audio, metadata, or picture, has its own checksum. So within the container format, it is able to verify that what you receive now is the same as what you are opening in the future. So that means you can verify that nothing has changed. You can prove the authenticity, the integrity of the video container. So some of these plus points for why we chose this format as the container. And the last one is it supports technical and descriptive metadata, just like how it supports video, audio, picture, and subtitles. And the way it supports technical and descriptive metadata is that it essentially one line of command line where you can just add it in, like this is the metadata that we want to include into the file, and I will show what we have included later. So the focus, sorry for the long introduction, but the focus is the environmental impact. How did the choice of choosing FFV1 and KV as our format of choice for our preservation master, and how does it affect the environment, and can we quantify what is it that we are saving or we are trying to reduce? To be honest, when I started this line of investigation, I didn't know it is a big rabbit hole. It is very difficult to calculate because there is a lot of unknown processes that you just can't obtain the data that you need on what exactly is happening to calculate the exact environmental impact. But I gave it a go, so you get to see what's happening. And the idea is very simple, right? Lossless compression reduces environmental impact. You have less storage space, smaller files to check, less energy consumption. Because one of the things about preservation or storage is that you have to keep checking it to make sure that it's the same. You know? All kinds of reasons why that is necessary. And the largest piece of energy consumption is when you check it, right? And checking it requires you to use checksum, which is a signature when you process the whole file and you spit out a string of numbers that is uniquely to that file, and then you can use that value to cross-check. So every time, every period of time, let's say 6 months or a year or even daily, you will use that number and run the same process and check, is it the same? If it's the same, great, nothing has changed, very good. But every time you run it, you are consuming energy. And that sort of lead to carbon dioxide equivalent emissions, and it costs money because of energy consumption. So the calculation that I do is very specifically to our organization and how we are doing our fixity checks. And there are 3 types of fixity checks that I have considered significant enough to put into my calculation. Number 1 is the file movement fixity checks. Whenever the file is moved in our storage system, it checks the checksum fixity to make sure that the movement is safe, that everything from point A to point B is the same. So that's 1 fixity check per move anytime you change the location. And then there is continuous fixity check in the storage layer. This is an appliance function where it will keep checking the files when it's sitting there in a periodic function, periodic frequency to make sure that everything is still the same. And then on top of that, we also have an annual, or we try to make it annual, entire holdings fixity check. And this check, we are running it for 3 different checksum type, CRC, MD5, and SHA-1. And upon ingest, these 3 checksum would be created, stored together with the content, and then every year we will run everything through and check that everything is the same. The answer for the annual fixity check is that every year we found something that is not the same. So that is another talk entirely together. We can just say that we are glad that we are running that kind of check, because a lot of issues have surfaced when we are running fixity check annually. And because we are keeping 2 copies of everything, that automatically doubles the fixity checks that we are running, because you have to do it twice, 2 copies. So this is the calculation. A lot of assumptions, but file movements fixity check estimate about 4 terabytes per day, and that is, I guess, is a unique thing to our architecture, where we have a storage intermediate layer, and then every day you will sort of empty it into a different layer. So kind of 4 terabytes a day, and it generates about 0.00533 kg CO2 equivalent per day, and 1 year is about 1.9 kg. And continuous fixity check, this is the automated function that runs every day by itself, estimated about 20 terabytes of data that you crunch through. 0.0266 kg CO2 equivalent, 1 year is about 9.7. And then the annual entire holdings fixity check, 3 types of hash, 2 copies, about 700 terabyte, which is the amount that we originally have estimated for the digitization, about 5.6. In total, it's about 7 kg, right? And there are websites that you can estimate what it means to have 17 kg of CO2 equivalent. It's about 2,000 number of smartphone charged, 44.2 miles driven by an average car. The website that I use is the American EPA government website, so it gives you miles and gasoline. And the estimation that I use is from the New Zealand emission energy factor, where 1 kilowatt hour of purchased electricity is about 0.12 kg of CO2 equivalent. And when I say up to 50% savings, you can skip the assumption, up to 50% savings is, you essentially can see clearly that you are reducing by half the CO2 equivalent emission. So from 2,000 smartphone chargers to about 1,000 smartphone chargers, from 7 liters of gasoline to 3 liters of gasoline. So that is the benefit, right? So this exercise has quantified the savings more than just the cost. And I guess I can go into assumption. Do I still have time? There's a lot of assumption. How do we calculate? How do we calculate the energy consumption? We found some prior research that about 1 megabyte of hashing consumes about 40 millijoules, and then we did the conversion. It's about 1.11 to the power of -8 of kilowatt hour, and then we extrapolate from there. So that is a big assumption, because that paper was on security hashing and things like that, and then we basically just took their calculation and then extrapolate from there. And then we also assume that the power consumption is the same for all 3 different kinds of checksum type, which might not be. And we also use the lazy representation of 1 terabyte is 1,000 gigabyte rather than 1024. And we also assume that the power comes from purchased electricity, which is a big assumption because it could have come from other types of power that you generate. And then we also make a big assumption that the emission factor is the same all year round. What we have discovered is that the emission factor changes, and each country would naturally have its own calculation, but this is the New Zealand calculation, and they have a monthly emission factor. How much of the energy consumption is equivalent to how much of CO2 emission. Yeah. And so this is the result, and we are quite happy with it, and this is the environmental impact component. Of course, we also take into account all the other challenges of choosing this lossless compression format, because we're changing it, right? So complexity is one of them. When we have compression, you are essentially transforming the signal of or the data of what you have originally into something else. And lossless compression means that you can actually go back, but it does, that action itself already introduces change. So naturally, as archivists, we are like conservative, as like, hey, there's a change. Is it actually safe? But my argument is that if the change introduces, provides us with the benefit that we want, the goal, and if we are able to understand what is actually happening and the complexity, then we can manage it, right? So we can be a bit more comfortable and less worried about what if we do not know how to get it back, for example. So that is how we were able to say that yes, there is compression, but it's lossless, and we understand it because it's standardized and it has adoption by other institutions. So hey, you know what? It is okay. There is also 2 other challenges with FFV1 NKV, which is that they are not very good at handling timecode, and not like the MOV format that we used to have, where it basically records the time code throughout the whole format. So the workaround that we have is that instead of trying to replicate the function, which is currently not fully supported, we actually did the time code of the first frame, and then you can extrapolate what is the next time code, etc., etc. It's a workaround, but we are okay with that because the content that we have in our holdings don't really have a lot of time code materials. We are not a broadcast archive, so it is okay. And again, because we are not handling broadcast materials, there is not a lot of closed caption or subtitles. So we are okay with this not 100% support for closed caption or subtitles. I will keep going ahead. The other thing that sort of came as a, I guess, not surprise, like a plus point for after we chose this format is that we were able to include metadata, and we were wondering, one of the things that we were trying to do is to record the digitization provenance. In the SAMA system, it actually produced an XML right, at the site for the digitization provenance, and then you would have to keep the file and the sidecar together. But we were thinking, can we put it into the file so that it exists as one entity? So that's what we did. So you can see on the table the list of all the things that we have included into the header of the file, and actually we just took it from the broadcast wave format. If some of you are working with audio, you might recognize some of this, and then we tweak it, and then we say, I think Bex is doing a good job in how they describe digitization provenance. We will just take it and then put it into video. So that's what we did, and this took a while because it's something new. No one, from what we understand, no one else is doing this way using MKV. So the vendor was a little bit hesitant, but we say we still want it because this will provide us the provenance at the point of digitization, and this means if there's anything, we can always trace back to just the file rather than having to look at another file. So this is one of the plus point, and this is how it looks like when you use media info to interrogate it. Took a long time to get to this stage. A lot of to and fro with the vendor to just get this exactly what we want. Surprisingly, yeah. And actually this is the end of my talk, and these are the resources. Did quite a bit of literature review to try to find how to calculate the environmental impact, and I would strongly recommend reading the Pendergrass article. It is a very, very detailed article about environmentally sustainable digital preservation. And that's it. Thank you very much.
Well, before, just to kind of wrap things up, I'm going to just give a few observations that I made during our four really enlightening and wonderful talks. You know, that really highlight the importance of science, engineering, and innovation, and utilizing innovation and work that's been done across different industries and leveraging that for our own help within AV archiving and film preservation. And throughout all the talks, we're seeing advances and technological advances that also, you know, face issues that many of us within archiving are dealing with daily, with knowledge obsolescence, the difficulty in training and high learning curves and introducing new students and new practitioners into the field, whether it's, looking at things that have long been considered, canon within our field, whether it's RGB scanning, whether it's the use of molecular sieves, the use of uncompressed files, or quality control that has been developed either for the broadcast world or is, complicated to the point where, it's not within the reach of the archivist working day to day. These are all things that that may at first seem, these are expensive or high tech, but at the end of the day, the expense that you're saving by doing a lot of that and using a lot of these developed technologies it outweighs the oftentimes expense that comes with long-term high learning curve staff training, and it gives archivists the opportunity to do more archiving and more providing access to materials, because we're being able to leverage technology in a way that helps us, and we are very fortunate to have experts and scientists and innovators in the field. So I think we should all be very fortunate that the work of Jim, Bertrand, Joshua, and Peter can contribute to our field in such an innovative way. So those are kind of my just thoughts I had, and let's open the floor now for more comments or questions.
Questions for Joshua. So I think you clearly explained the benefits of going and moving to FFV1. So the first question is Archives New Zealand planning to retranscode all of its V210s into FFV1? And second, if archives are interested to do that, what's the best way to do, to retranscode its entire collection to reap the benefits of FFV1?
Good question. Easy answer. Before this massive digitization project, we have digitized very few, like a handful. Not some insurmountable task to actually even manually transcoding them to FFV, but if you want to. But one of the things about our digital preservation system, Rosetta, and the system was designed with migration in mind. And what we call it preservation action. If there is a preservation concern and we need to migrate the format, the system actually has the ability to migrate the format for us in like an automated bulk way. And not surprisingly, it's actually using FFmpeg. So it is actually built in as a plug-in into the digital preservation system, and this applies to more than just AV. This applies to every digital files that we have in our system. We always have the migration philosophy in mind and preservation action as what we need to take if it's necessary. So I guess that sort of answer your question. Yeah. You have one?
No, I have one for you. No, because you brought up a really interesting point, and it's something to discuss. It's one of those points that doesn't have a correct answer, right? And you mentioned quickly that the metadata, that you're choosing to put the metadata in the file as opposed to the wrapper.
Yeah.
And in the SAM system, we chose to use a CSV file. So why? And the reason is that when you have millions of files, the cost of time and energy and resources of unwrapping things becomes an issue.
Yep.
And when you put the metadata in the file, you have to go down 2 layers in terms of the unwrapping in order to make a change. So unwrapping just the wrapper and making a change in the wrapper is trivial, and the cost associated with time and energy. It's a project, right? And so if you're going to do a lot of fixity checks and a lot of that kind of stuff. Every time you do it, you incur that cost. So that was the decision that was made. There's not a right or a wrong, but I think I should tell you how crazy this can go.
Yes.
Because I was there at a meeting where it happened. Because some of you may have thought about this, like, well, okay, if what we're going to be putting in our metadata is basically our catalog information, right? Yeah, I see some nods. We're going to put the catalog information in the metadata, and that's going to go in either the file or the wrapper. You choose one, doesn't matter, it's the same problem, okay? Well, we were sitting around a meeting and someone said, well, wait a second. What that means is that if we lose our main catalog, that we can reconstruct our catalog by going back and getting all of the files that are in the system and reading back that information. At which point I blew a gasket and I said, no, actually the way to back up the catalog is to back up the catalog. That you don't want to add that much metadata in the file or the wrapper, whatever it is. So what evolved was a slim metadata choice for the wrapper and or the file, whatever, and being careful to intentionally not try to recreate the catalog, but to do things in the metadata for the file that relate to the file and that reference the catalog. It may sound like it doesn't matter much, but believe me, if you have 1 million files, all of that stuff becomes really important. It's a lot of work. I mean, we're talking about months of work. So I just wanted to mention that.
Yes, surprisingly, I agree with you. Not surprising. So the metadata that we have decided to include is only the digitization provenance metadata, which is, in this case, we felt that it is necessary because it's the one time, because we are migrating from a physical carrier to a digital file, and that process happened, and we wanted it to live together with that file. You are absolutely right. It can go crazy really quickly if we start putting more and more metadata, like the catalog and everything, and that kind of situation in my institution is kind of decided for me when I joined, because the digital preservation system that we have actually does keep a sidecar file using premise of all the actions that has ever been done on the digital object in the repository. So we have an XML that is uber long of every single action that we have ever done to the digital file, and some of these things are the catalog information, or whether we have done fixity checks or virus scan, and all of these actions are recorded because we want to prove that we are able to provide an audit, right, of what has happened. So it's not in the file, and I agree, we shouldn't make the file more complicated than the function that it has.
So in the specific example I'm giving, in the same meeting, I said to some of the people who asked for this were the catalogers, not surprisingly, because they really liked this idea. And I said, well, what happens if we realize that someone spelled Stanley Kubrick wrong?
Yes.
Okay, so it happens.
Yep.
You know, someone makes a typo. What happens? What do you have to do to fix that?
Exactly.
And you start going through all of the things you have to do it, and it's going to cost you a couple $1,000s to fix that. And so, why create the problem for yourself?
Agreed.
In the first place.
Yeah.
I have another question. Wasn't a question. I have a question.
Sure.
So you can look at doing fixity checks on different levels.
Yes.
Like how granular do you want to get? So you can do the fixity check on the wrapper.
Yep.
And if you haven't changed anything in the wrapper and you have a log on the wrapper and the fixity check on the wrapper is correct, then the stuff that's in the wrapper also should be correct.
That's the assumption, yeah.
Right.
Yeah.
Or do you unwrap everything, do the fixity check on all of the elements, and then rewrite the fixity information in the wrapper, right? Or, so, what did you guys decide? There's, again, no right answer.
That is a very interesting question, and yes, you're right, we can just do the verification from the header alone and assume that it is correct. But such functionality is non-trivial, it doesn't exist. It's like just checking the wrapper for this format, right? Like it's theoretically possible, but it is not so easy to implement. Because you are making a big assumption that the video streams and the audio streams are untouched, even though the wrapper information is correct.
Well, how are you going to get the video information if you don't unwrap it?
Run it through the whole thing, which is why I'm calculating the cost. But I mean, you have to, in order for you to generate the signature, you have to run it through at once at least. Yeah. So that is I would say unavoidable. But maybe after the first time you run, then maybe you can then verify the future with a less intensive process after the fact. But you have to still run it once.
That's what I would say, that you would be able to do the fixing check just on the wrapper, assuming that the wrapper hasn't been opened.
Yeah.
And you'll know that before you open the wrapper.
Mm.
You should.
Yep. Good.
Sweetie, I think, has a question, and then next,
I want
after
to
Sweetie,
pick up
but
asking the
You can take
question
a mic.
after Jim. So just give a quick question.
Because on the Jun's question, I think Joshua has the right opinion, because sometimes you need to make sure every bit in the file, in the rep. But I'm not sure, you mentioned that for the annual check, you check CRC, MD5 and SHA-1.
That's right.
Is that really necessary? And, because we all know that there are the probability for byte decay, but maybe you can say more about this.
Why did you ask this? The answer is that it is a policy that has been decided a long time ago, and it's because of collision, right? Because MD5 collision happened, you can't guarantee that there is no collision. So the policy is that therefore we have multiple types of checksum to minimize the collision risk. Collision, for the benefit of the audience, means that when you do a checksum, sometimes you have two files giving you the same checksum. So there is the risk of that, because they are all mathematical calculation, and then you might get one checksum for two different files. It's a large number, 1 upon how many million, but it is there for MD5. So therefore the decision was to say, okay, let's just do 3 different checksum, then you kind of like minimize it. There are better ways to do it now. Okay, but it requires a lot of modification to the system that we have right now. Working on it.
I think because I think about this question, whether the probability is too low to do that.
Yes.
Even MD5 is enough. You don't need to SHA-1. If you really want to avoid this problem, you go SHA-256.
So what you have just said is indeed one of the consideration or like a conclusion that we can take, and I think this kind of decision is important, because you evaluate the probability and then you decide on it, which is also my preference of deciding. You know that there's a compromise, and then you just have to accept the risk. But just like when I talk about compression, sometimes we take a very conservative line drawn, like say, if there is even 1 in 10 million, it is still something, let's just draw the line further away, without knowing the actual cost. So it's not that my predecessors made a wrong decision, but it is, I would say, a philosophy on how comfortable you are with risk. Because digital preservation, at the end of the day, is risk management, right? You manage all the risks that you know, and you try to minimize the things that you can control. And checksum is one of them. Yeah.
I believe Sui had a question.
Yes.
I was actually going to ask sort of that same question.
Okay.
Because since you're doing all three kinds of checksums, have you seen any benefits yet in using all three, or it really doesn't matter?
It helped us when this is not my talk, but sure we can talk about this. And when we do our annual fixity check, the three checksums that we have helped us in cross-checking, right? I didn't go into too much detail, but when we do our annual fixity check, what we have discovered is that there is a lot of errors. We have actually classified error 1 to error 9 on different types of error that we encounter when we run the annual fixity check. And one of them is I/O error, which is like the storage that we have couldn't keep up with the kind of checksum that we are running, and then we keep getting this kind of error. So we rely on other checksum that we have in the database to cross-check that actually, you know what, the checksum is okay, it's just that the storage couldn't keep up, the database couldn't keep up, things like that. A lot more complexity under the layer. Yeah.
There's fundamentally two different kinds of errors. One's a hard error, and the other is a soft error. Okay, hard error are generally hardware errors. So the thing that's interesting about that is that, when most people have their IBM PC, you'll never run into a hard error, right? Because your input or output, during the course of the computer is, for most people, half a terabyte or a terabyte maybe. During the life of the computer, you're looking at web pages and doing word processing, right? When you're moving around a petabyte and a half, that's your storage, and you're doing the reformatting. So you're moving like, I don't know, I'll make a number, 10 petabytes a year, 20 petabytes a year. You will have hard errors.
Yes.
Okay, because the disk controllers aren't, they'll tell you what the error rate is, right? Manufacturer will. And so if you actually do the math, it's like, depending upon how big your storage is, you may run into a hard error like once or twice a week, right? And if you're moving stuff a lot, if you're doing like what you're doing, if you're doing all the fixity checks, I mean, you'll probably create errors while you're doing the fixity check.
That's right. Exactly that. And because we are running our fixity check, we actually discovered the limitation of the hardware that we have. Yeah, it's because we did the fixity check. No one want to ask me about the environmental impact. That's the purpose of my presentation. Anyone have tried doing similar calculation?
I have.
Yeah.
I had to.
Okay.
So I was designing a facility, and so I had to figure out how much air conditioning was required. And in order to figure out how much air conditioning was required, you had to figure out how much storage you had, and how many, and how many amps that draws. But in that case, what you do is you don't do it quickly. You did it. You just add up all of the amperage of the equipment that's being used, and then in the U.S., the amount of amperage that a circuit will handle is only a maximum of 80%. So in other words, if you have a 10 amp circuit, you can't run any higher than 8 amps without tripping the circuit. So if you work backwards with the amount of current, you can't use any more than 80% of the 20 amp circuit you have. So therefore your maximum air conditioning draw is that, and the BT is generated by that. You can't use any, which you can't generate any more heat from that amount of energy. And so that's how we did it.
Yeah, that's the benefit of actually having all the control of, like you have access to this data, like even the amperage and everything. The storage that we have is a managed storage, so it is with the vendor. So like you can't get this kind of detailed information from them. So a lot of estimation.
The problem with doing it the way that I just said is you end up with a lot of extra air conditioning. No, you do. Because what you're doing is you're creating the amount of air conditioning that would be necessary if you ran everything at the same time. And of course you don't.
Yeah.
So then what you do is you multiply a factor of utilization, and the way you do that is you figure out what your target workflow is. Okay, so if the maximum draw is, 1,000 kilowatts, let's just say, okay, that's if everything is running, but you know that the night shift is only going to have half as many people, and the scheduled workflow is half as much, then you can scale back on it. You can do that.
Okay.
You have a question?
Any other questions? I'm going to ask Peter a question. Can you hear us?
Yes. Hi.
Hi, Peter.
Hi from Europe.
What is in terms of training and learning curve for utilizing the VidiCheck system? Is it something that is low, medium, high level of pre-knowledge of well, we're talking about film specifically, but for those of us, for example, who might use students or people that don't come from a film or broadcast environment or any type of even film archiving environment. How do you feel?
Okay. When I understood right, you're asking whether there is deep learning curve necessary for people who are doing quality control for preservation, digitization. Yeah. Okay.
Yes.
Yeah. I would say there is, of course, some knowledge necessary by the people who are operating, doing the QC. Mostly, they need to get some experience, or they need to have experience about the media. So about, for example, in these 3 film projects, most of the issues are media specific. Of course, there are also issues which are coming from how things are operated, but you need to have an understanding how the media works, so that perforation can break or that the light is wrong. So also you need to get some knowledge over time. This is not there maybe in the beginning always, but in the first weeks or months, usually these new operators get the knowledge by running the workflow. Of course, they need some background knowledge. So ideally, they are coming from the audiovisual domain, doing some work on audio, video, images before. So that helps a lot. So the media is the most important thing. Concerning learning how to do quality control with specific software like ours is, so this is, I would say, yes, it's training. It's 2 days training, and after some 2 weeks, we're usually making another reflection round to see what happened and how they are able to work with the system. But that's quite steep. It's a quite easy way. But that's the easy part. But some background knowledge is necessary, yeah. On the media.
Great. Thank you, Peter.
Yeah, you're welcome.
Peter.
May I add one point concerning the metadata discussion before, whether descriptive metadata are inside and outside. So I fully agree, descriptive metadata should not be in a preservation master file. This just makes hassle in the future. What I want to mention is one point. When looking to the preservation master files itself, so into the file, it's important that the technical metadata in the file on the different levels are consistent. So we had one project where actually the wrap information was not consistent with the information in the bitstream. In this case, it was the GOP structure information, since they used the 15-frame GOP structure. This was wrong, this was not consistent. And this caused at the end that the decoders of most vendors behaved correctly, since it behaved correctly, so they produced blocking. So if you want to prevent in future issues, make also sure that besides checking image and sound, checking also that the standard compliance is there between all the levels in the file. So from the wrapper the GOG information in the bit stream and going down is consistent. It's the same with if you have video with interlaced upper field first versus lower field first, and that kind of stuff.
Thanks, Peter. That's one thing I didn't really talk about in the presentation, which is that exactly that the technical metadata of the format. So one of the things about FFV1 MKV is that it has something called media conch, which is basically a validation software that checks exactly what you say, like whether it conforms to the standard of how it should be.
Yeah.
And you also can configure the particular fields that you are interested in to check. And for the project that we are doing, we have requested that the vendor do that. So we give them the profile, and then they would have to make sure that everything passed before they deliver it to us. So sort of one of the things that we are checking. Yeah.
Hello. I've just had a question for Peter, and that's about VidiSearch, and I was just curious to know how it deals with the possibility of false positives.
Do you have maybe a microphone? I hardly hear you.
The question is about how VidiSearch deals with false positive.
Yeah, so that's always a question with any QC system, of course. What we try is first to bring down for each of our detectors we're developing that rate to a level that it is more beneficial to use the system than to check for false positives. So that's the main thing in the design phase of our system. Of course, this is possible with many of the defects which can occur. This is not possible with any defect today, I think. And this is also the reason why we are having an approach which allows for validation, and not just for validating the things which are found automatically, but for giving an operator also information about how relevant the detection was in their analysis phase. So how likely it is a severe issue or not. And if you have that information, whether it is likely severe, you can rank the list of issues you get out of the analysis phase, and you're starting with the most likely severe ones in the interactive validation. And after a few detections, you already have a feeling about what is going on. That's digitized media. Of course, maybe to mention is also important. The stronger the defects are, usually the more safe are the decisions or assumptions made in the analysis phase. So by having that approach, you are checking 5 or 10 detections from the automatic analysis, and you get already a good feeling if there is an issue or not. Of course, in the list below there would be many more detections, smaller, minor ones, and the likelihood that it is many small detections, there are also false detection, that's right, that's there, but you don't need them, so that's the clue for making a decision, since it's always a compromise to make quality control also in a time-efficient way. Our approach is to this relevance-based approach, checking for the most likelihood severe issues first, and making that possible for a QC operator. And of course, there's always a second part. The operators are really looking through different visualizations of quality measures over time. If you have, for example, unsteadiness or flickering or dust, if you are a bit trained, you very quickly can decide whether there is a systematic issue. For example, if you have unsteadiness just in a few shots, that's not a problem, but an issue for digitization, of course. But if you have a continuous unsteadiness level, you probably have a problem. How the scanner was configured or parameterized.
Hi, Peter.
Hi, Jim.
You know, sometimes we look at the world through 2023 glasses, and we forget that, like in the case of film, they punched the sprocket holes, right? And they weren't always accurate, and there was tremendous variation over time as they were punching the holes. Sometimes the metal punch wore out, and it wasn't quite as sharp, and it wasn't quite as accurate, and you actually look at the standard of, in SMPTE, they have the standards, and Kodak as well, and you'll see quite a lot of variation as being acceptable. So it becomes really interesting in terms of quality control, in terms of what's an error and what isn't, in terms of false positives, because what's a false positive if you bought Kodak film today versus Kodak film that was made in 1950, you know, it's the standards have changed, and the manufacturing ability has changed. So, you know, in my perspective, it's more about statistics, really. It's like statistical probability. You have a, you know, if you try to look for a specific sprocket hole and go, aha, that's a bad sprocket hole. Yeah, sometimes that'll happen, but you get a lot of false positives with that kind of stuff, and it's because of the way the media is. You know, that's just the way it was.
Yeah, thank you. Yes, that's right. So of course, the quality standards over time changed with the different films and film stocks and how they have been processed. And I think that's also part of the knowledge which is required by QC operators, that they know what they can expect in terms of quality from a certain period of time of film. Yeah. So that is necessary. Yes. Yeah.
Okay, we are out of time. There's this concluding session in the main ballroom, I believe. But let's give a big round of applause for an